Hey, Tao Penalized Math Industry, and we're gonna do math with levers. So in this video, we're going to introduce you to a simple machine that can help you with lifting and hauling things, and it will decrease the chance of a back injury. But how do levers work in the first place? Levers are actually easy to build because what you'll be needing is a fulcrum, something that will hold the beam or the plank in place. The fulcrum is actually what can go in the middle, and this long piece is actually going to rest on top of the fulcrum. And it's going to go on top of it. Now we have produced a lever, and the reason why that it's a triangle prism for the fulcrum is because the lever can move just like this, back and forth. But levers cannot work unless they have a load on it. So here in Super Mario Maker, we have a lever. And what we can do with this lever is put items onto it. So let's put Mario right over here and place a POW block over here. And it'll balance. If Mario was in the real world, he would weigh around 90 kilograms. And we can also say the POW block also weighs 90 kilograms because the lever is balanced. We can determine this with a formula. The formula is, if the lever is balanced, then that means the force or the load multiplied by the distance from the fulcrum is going to be the same thing as the force on the other side of the lever multiplied by the other side of the distance from the end of the lever to this fulcrum. So, if the numbers that we get are the same, then that must mean the lever is balanced. But if the numbers are different, the bigger number, or the number that's greater, is going to be heavier than the one that's lighter. So it's going to be unbalanced. Why do we measure the distance in the formula? The reason why is when you're using a lever, the object that you put on the lever doesn't have to be the same place where the object that you put it on one side and the other side. You don't have to put an object at 4 and the other object at 4. You can actually put an object at 1 and 3, for example, and it will still balance. Here's an example. So, in the last example, we had two objects, Mario and the POW block, placed at the same point on the opposite sides of the lever. So each block or each square, 1, 2, 3, and so on, is going to represent the distance between the fulcrum. That gold thingy in the middle is the fulcrum, holding the plank in place. So if it's easy for Mario to actually haul and lift one POW block, but what happens if he wants to haul 4 POW blocks? What Mario will have to do is he'll have to move the 4 POW blocks to the closest as possible to the fulcrum. So if we move that over here, it'll be easier for Mario to lift it by going over here, because the bigger the lever is and the closer your object that you're trying to lift is closer to the fulcrum, then the less force is required in order to push it up. See, it's actually easier for Mario. We said that each POW block weighs 90 kilograms, and Mario also weighs 90 kilograms. Let's do the math. So, if the lever is balanced, then we have to multiply Mario's weight with the distance between the fulcrum. And the power block's weight with the distance between the other side of the fulcrum. So, since we knew that each square of the grid is one space in the game, then Mario was 7 spaces from the fulcrum, and he weighs 90 kilograms, so as the 4 power blocks, but they're at different places. So, 0 times 90 is 0, 0 times 90 again is 0, but 90 times 1 is 90, and 90 times 1 again is also 90. So if we add these two up together, we get 180 on this side of the lever. That is how much force for kilograms is being applied to push down on it. Let's see what Mario is. So, if Mario is standing on 7 spaces from the fulcrum and he weighs 90 kilograms, that means he has to be 90 multiplied by 7. That is going to be 630. So pretty much 630 kilograms of force being pushed down on the lever. So 630 and 180, do they equal? I wouldn't think so, because 630 is actually more than 180. Therefore, Mario at this part of the lever actually weighs more than the power blocks. With the larger lever, it actually gives you an advantage. The larger the lever is, the less force applied that you need in order to get something up that you want. Let's see an example where something is balanced rather than unbalanced. In this example, we now have a bigger lever, and Mario wants it balanced this time, and he wants to use a bullet bill launcher. That is a machine that can shoot bullet bills at Mario. So if we place it at 3 spaces away from the fulcrum, 1, 2, 3, and if we place Mario at 6 spaces from the fulcrum, 1, 2, 3, 4, 5, 6, then will this lever be balanced? Let's do the math. So, if Mario stood at 6 spaces from the fulcrum and he's 90 kilograms, and the bullet bill launcher machine stood at number 3, targeting at Mario, then will this be balanced? Pretty much. Let's try it. 6 multiplied by 90, that is going to bring us to 540. And 3 multiplied by 180, that will also bring us to 540. So, is 540 equal to 540? Yes, which means that this lever will be balanced. Those 2 examples can show you how you can use math in levers, and those are the only 2 examples. You can actually experiment with this and actually have different items in the game, so you can experiment, like Mario with a power block and a muncher. Are they the same? Yes! And there are many other combinations. Why don't you try them at your home? Comment below what you have learned about this video and what combinations you've tried out. I hope this video has helped you understand the mathematics with levers. Thank you for watching Taoping Airlines Math Industry. Like and subscribe. And to end the video, let's see Mario try to jump over a thwomp after hitting a lever.
Oh.